Hi, welcome back to another lecture on space robotics. This time we're going to cover thermal control subsystems. Just like the other subsystems, my goal today is that you'll be able to define the function, typical requirements, design considerations, and verification methods associated with various technologies in a thermal control subsystem. Let's look at this critically important but often invisible subsystem, the thermal control subsystem. This subsystem's primary job is to maintain all components within their allowable temperature ranges. You may ask, why does that matter? Most spacecraft electronics, batteries, instruments, and even structural adhesives only operate within a narrow thermal band. Outside that range, things fail, drift, or die. So let's walk through what you're seeing on this slide using a Mars rover as an example. This rover uses a radioisotope power source, the MMRTG, which produces power but also heat. That waste heat is distributed through the body using these tubing networks, labeled CHRS and RHRS, or Controlled and Radiative Heat Rejection Subsystems. They flow heat between the hot plates and the cold plates. The rover's internal components like batteries, avionics, and instruments are mounted on these thermal plates, which regulate how much heat each component receives or sheds. Below, we zoom in on the panel structure itself. It's made of a sandwich composite of aluminum face sheets on either side and a honeycomb core filled with aerogel in the middle. This gives it high structural strength with excellent insulation, ideal for keeping internal heat in or the Martian atmosphere cold out. Mars gets cold, really cold. The Martian night temperatures drop below -100 degrees Celsius, especially near the poles. So the thermal subsystems must insulate vital systems, store or circulate waste heat, and sometimes even intentionally radiate heat away during the day to prevent overheating. In your own missions, you'll need to consider what is the expected temperature range at your destination. Do your payloads require active or passive thermal control? And how are you going to route or insulate heat from internal sources like power systems or actuators? When we think about thermal control in space, it's easy to imagine heaters, coolers, or thermostats. But at its most fundamental level, the spacecraft is a thermal conduit. It's not generating energy, it's balancing it. This slide shows the key players in the spacecraft's thermal environment. First, we have solar radiation. This is the direct energy coming from the sun. It's the largest single source of heat input for most spacecraft. Then there's albedo radiation, sunlight that reflects off of a planetary surface like Earth and bounces back towards a spacecraft. It's less intense than direct solar radiation, but still important, especially for orbital missions. We also have planetary radiation, in this case Earth. Like any warm object, it emits infrared radiation. This adds more heat input, especially to surfaces facing Earth. All of this energy is absorbed by the spacecraft depending on its surface properties, like color, finish, and coatings. On the other side of the equation is radiation to outer space. In the vacuum of space, radiation is the only way to get rid of heat. There's no air for convection unless you have some kind of atmosphere, and minimal conduction unless you're touching some surface. The spacecraft re-emits thermal energy based on its temperature and surface emissivity. So the job of the thermal subsystem, especially its passive function, is to balance all of these flows. It must make sure that enough energy is rejected to space to avoid overheating, and that enough is retained to avoid freezing. That's why we call it a thermal conduit, balancing solar gain and radiative loss. It doesn't create heat, it manages the flow between the environment and structure. When designing thermal systems, we can't assume a single space environment. Every planetary body has its own unique thermal profile, driven by its distance from the sun, atmosphere, rotation, and surface properties. Remember this picture of the different environments that we're thinking about? This is a visual callback to how different planetary surfaces look, from Earth's breathable atmosphere to Titan's dense haze and the Moon's exposed regolith. On the right, we see temperature ranges of major solar system bodies. Some, like Mercury and the Moon, show extreme swings due to a lack of an atmosphere. Others, like Titan and Venus, not shown in this chart, have thicker atmospheres that insulate them. This wide range, from below 100 degrees Kelvin on asteroids to over 700 degrees Kelvin on Venus, means that thermal subsystem designs must be tailored to each mission. Your thermal solution for Earth orbit won't work on the lunar surface, and it definitely won't survive Venus. So the takeaway is, know your environment. Thermal design starts with understanding where you're going and what temperatures your hardware will face. Thermal design is a cross-disciplinary process that pulls in constraints and inputs from almost every other subsystem. It starts with defining requirements and constraints, where the spacecraft is going, what orientation it will have, and what each component needs thermally. From there, thermal engineers map out the transport and control methods, like coatings, insulation, heat straps, radiators, and active coolers, all while integrating feedback from mechanical, power, and electronics teams. Once the thermal layout is defined, the design feeds into mechanical drawings, part procurement, and hardware installation. Finally, it's verified through testing, thermal vacuum, thermal balance, and model correlation, ensuring that the system performs as predicted in flight-like conditions. It's an iterative, system-level process and critical for mission success. In the rest of the presentation, we're going to talk through the sequence of design activities with illustrative examples that I want you to follow in this week. One of the first steps in thermal design is gathering the temperature limits for every single component in your robot. What you're seeing here is the thermal requirement database for the TerraSAR-X spacecraft. Every row represents a different subsystem or component: radios, sensors, electronics, batteries, even structure. For each item, we define two thermal ranges. The operating range, this is the temperature range the component must stay within to function properly. And then the survival range. This is broader, and it defines the temperature limits the component can safely endure when it's not in use. In this bar chart, black represents the predicted operating temperature. White shows the allowable operating range, and pink adds the full survival range. The blue background gives visual context to where components fall across the spectrum. You'll notice components like the battery, IMU, radios, and onboard computer tend to have tighter limits. These are your most sensitive parts and often drive your thermal design strategy. This chart also shows why thermal design is complex. You don't design for just one range, you must consider every single component, ensure that it survives extremes, and remains functional during operations. I'm going to ask that you keep track of your components for your space robot design requirements for this course. When we think about thermal control in spacecraft, we usually think about protecting components, keeping batteries warm, or cooling optics. But for space robots that are designed to interact with external matter, the thermal subsystem often needs something much more active. It needs to change the temperature of what the robot touches. These are what we call thermal targets, materials in the environment that must be heated or thermally stabilized to achieve mission goals. This is not common for satellites. It's a distinctive challenge for space robots doing science or resource utilization. Take MOXIE on the Perseverance rover. It's not just sensing the environment, it's processing Martian air, extracting oxygen from CO2. That process requires heating the electrolysis stack to around 800 degrees Celsius and keeping it there. That's a real thermal requirement. Maintain stack hot zone at 800 degrees C plus or minus 25 degrees C for at least 1 hour. Now compare that with Trident, the drill planned for lunar volatiles. If you want to analyze ice mixed with regolith, you can't just dig and sniff. You have to heat the soil and sublimate volatiles like water, CO2, and nitrogen. That gives you a target conditioning requirement like raise regolith core to 150 degrees to 300 degrees C for volatile release. These are special requirements. They reverse the usual thermal problem. Instead of shielding payloads from extreme temperatures, these systems create and control extreme temperatures in their targets. In these two cases, they show up in situ resource utilization, surface chemical analysis, and volatile detection, also science experiments involving reactions. So when designing thermal subsystems for these kinds of missions, you're enabling the mission by deliberately manipulating matter through heat. Before we can design a thermal subsystem, we need to understand the environment it's going into. Earlier, we talked about how not every environment is the same, but now we'll talk more specifically that we need to calculate the external heat sources and expected temperature extremes at our destination. So this plot that we saw earlier you can see that there are different ranges for these different bodies in our solar system. These ranges help us determine the maximum and minimum temperatures our spacecraft might encounter. On the right, we see how solar intensity, which is different than temperature, drops off sharply with distance from the sun. Mercury receives over 6 times more solar energy than that of Earth, while Jupiter just gets 4% and Pluto only 0.1%. This plot tells us how much heat input to expect from solar radiation, a major driver in thermal balance. Together, these plots define the thermal boundary conditions for your mission. Your next step is to combine these external factors with your spacecraft's internal heat sources to estimate the equilibrium temperature and decide whether passive thermal control is enough. To continue the conversation about space environments, let's talk about solar exposure. Solar exposure becomes one of the most critical design drivers for your thermal subsystem. Speaking of space environments and their impact for thermal design, we need to get a little bit more specific about solar exposure. And when I say specific, I mean where exactly the spacecraft is on a planetary body. Let's take the lunar surface as an example. The plot on the top shows surface temperature over time at different latitudes on the moon, which are color-coded. In red, we have latitudes near the equator to nearly the poles, which are in blue. At the equator, surface temperatures can swing from almost 400 degrees Kelvin in sunlight to below 100 degrees Kelvin at night. That is a massive thermal load to manage. These swings follow the lunar day-night cycle, which is about 29.5 Earth days long, meaning long-duration heat-up and cool-down phases. As you move towards higher latitudes, the peaks flatten out and the temperature ranges narrow, like in this dark blue. You start to see these long eclipse durations. Especially near the poles, there are periods where the sun is intermittent or completely absent, which presents unique challenges for thermal storage and power systems. If you look at these lower images, these maps show maximum surface temperatures near the lunar South Pole in summer and winter, based on real data from NASA's Diviner instrument. The blue regions indicate permanently shadowed craters, where sunlight never reaches. Temperatures can drop as low as 25 degrees Kelvin, colder than anywhere else in the solar system. Just outside those craters, some crater rims receive nearly continuous sunlight, maintaining more moderate, stable temperatures around 220 degrees Kelvin. These sharp contrasts in temperature over very short distances mean your lander or rover could be experiencing radically different thermal conditions depending on where it's placed. For spacecraft designers, that means latitude and local topography must be factored in from the start, not just for survivability, but to ensure science, instruments, and batteries can operate at all. In summary, thermal design is highly location and time dependent, especially when your mission is trying to explore or survive at extreme latitudes like the lunar poles. In thermal design, geometry and component placement within the robot strongly influences how heat is absorbed, conducted, or radiated. In all 3 examples on this slide, we can see appendages like wheels or solar panels, antennas or arms tend to experience the most extreme temperatures. These parts are farthest from the spacecraft's thermal mass and are often in direct contact with the environment. For example, in the Moon Ranger thermal analysis, the solar panel is bright red, over 350 degrees Celsius, because it's directly lit by the sun. In contrast, the wheels touching the cold lunar surface drops below -90 degrees Celsius. These gradients could pose a risk to actuators, motors, and thermal interfaces. Meanwhile, the internal electronics like batteries and computer boards are housed deep inside the chassis, where temperatures are far more stable and easier to control, typically kept between -10 degrees Celsius and 35 degrees Celsius. This is a deliberate design decision for thermal protection. Some components, like radio transmitters or propulsion systems, naturally run hot or emit energy and must be thermally isolated or managed carefully, like the antenna for this satellite and the rocket plume nozzle on this lander. Finally, orientation matters. Solar exposure changes based on how the spacecraft is tilted relative to the sun. For missions at the lunar South Pole, where sunlight is low on the horizon, panel orientation is critical. Moon Ranger's panel setup is a good example of using geometry to optimize both power and temperature. For regulating the temperature of your space robot, you may consider passive or active thermal control elements. Passive thermal control means managing heat without consuming electrical power. These methods are reliable, lightweight, and are often the first line of defense for thermal regulation in space robots. First, on the left, we see a diagram of surface coatings. Coatings affect how much energy a surface absorbs versus emits. The ratio of absorptivity to emissivity changes the equilibrium temperature of a spacecraft. For example, a shiny metal surface might reflect most sunlight but retain internal heat poorly. These coatings are useful when you want to minimize solar heating, but still allow for radiative cooling. Next, at the center, we have heat straps. These flexible copper elements conduct heat between components. They're used when temperature must stay uniform between two locations, like from a hot circuit board to a cold mounting plate. The image shows real examples of varied shapes and terminations. Designers customized these to bridge thermal gaps without introducing mechanical stress. On the right is a simplified diagram of multi-layered insulation, or MLI. MLI blankets reduce heat loss by bouncing radiation between reflective layers, trapping it near the source. You'll see MLI as the gold or silver blankets wrapped around spacecraft components. They're essentially minimizing heat exchange in vacuum, especially for electronics or stored fluids. At the bottom, we have a photo also showing a radiator. Radiators are surfaces designed to emit heat efficiently to space and are usually painted black to maximize emissivity. They're used when you have steady excess heat to reject, common in power-dense systems or long-duration missions. Together, these elements, coatings, straps, insulation, and radiators, are passive tools for shaping the spacecraft's thermal behavior. Use them when you need simplicity, reliability, and no moving parts, especially in deep space or power-limited missions. Active thermal control uses powered devices to maintain spacecraft components within their operational temperature ranges. These systems consume energy, but offer greater precision and responsiveness than passive methods. First, let's look at heaters. The top left image shows a Kapton foil heater, a lightweight, flexible patch with embedded resistive elements. These are mounted to critical components like batteries or tanks and apply heat directly. These are common in vacuum-exposed electronics or small form factor systems where passive warming isn't enough. Below the heaters, we have thermostats. These are mechanical or electronic switches that turn heaters on and off when a set temperature is reached. The round metal unit is a space-rated thermostat used in satellites and launch vehicles. The household thermostat is shown for intuition. It has the same function, but this one is aerospace grade. You're likely to use thermostats when you need autonomous temperature regulation without a full control system. At the top right, we can see a cryocooler. Specifically, this diagram is of a Stirling cycle split pair unit. Cryocoolers provide deep refrigeration below 10 degrees Kelvin for sensitive payloads like infrared sensors or detectors where passive cooling isn't enough. These are complex, power-intensive, and reserved for high-performance science missions, like the James Webb Space Telescope's MIRI instrument. Last system I want to talk about is called a louver. Louvers are variable area radiators. They have blades that open to increase heat rejection and close to retain warmth. This drawing explains their mechanism, and the photo over here shows a real spacecraft, New Horizons, with louvers circled in red. Use louvers when you need to shed variable heat loads without active computation. Together, these active elements, heaters, thermostats, louvers, and cryocoolers, give spacecraft precise tools to handle variable, dynamic, or extreme thermal conditions. They are essential for missions with sensitive instruments, irregular power profiles, or changing thermal environments. The thermal control subsystem doesn't work in isolation. It has to interface with nearly every part of the spacecraft, and New Horizons is a great example of how that integration plays out in a real mission. This spacecraft had to operate not just in deep space, but eventually in interstellar space, with minimal sunlight, wide thermal swings, and limited power. That required a combination of passive and active technologies carefully distributed across the vehicle. Let's walk through some of the thermal elements and the subsystems they support. The RTG thermal shield and thermally isolated mount manage the heat from the radioactive power source. This is a structural and power interface, ensuring that the RTG doesn't overheat nearby electronics or radiate unevenly. Thermally coupled REMs, or remote electronics modules, and the thermally coupled tank show how propulsion, power, and avionics all depend on thermal design. These require stable internal temperatures for proper function and longevity. The RF switch panel radiator, the LORI radiator, and the ST assembly radiator cool specific payload and communication elements. These are interfaces with comms and science subsystems using surface geometry and radiator placement to ensure heat rejection. The shunt panel handles excessive electrical energy and dumps it as heat, so it directly interfaces with the power subsystem and becomes a thermal load in itself. The louver, shown near the payload bay, is an active thermal control element. It automatically opens and closes to regulate radiator output. The MLI blankets on the back of the high-gain antenna provide passive insulation, a structural and comms interface protecting the spacecraft's largest directional surface. All of these technologies are spatially distributed and tightly integrated with subsystems like power, comms, propulsion, and science instruments. The job of the thermal subsystem isn't just to keep components safe. The job of the thermal subsystem is to enable every other subsystem to operate reliably across environments that no human spacecraft had ever encountered before. New Horizons shows us that thermal design is a system-level challenge. Once you've mapped out your thermal design, and let's say you've picked all the technologies that you want to incorporate into your thermal control subsystem, it's useful to do a quick back-of-the-envelope check of your system's equilibrium temperature using a point mass approximation. This quick calculation treats the spacecraft as a single uniform node, one temperature, one set of inputs and outputs. It's a loose approximation, but a good sanity check before you go into complex multi-node thermal models. This first equation up here shows the total heat input of the spacecraft. Qin is equal to the sum of Q sun, Q moon, Q earth, and Q internal. Q sun is the direct solar radiation, which is typically the biggest contributor. On the lunar surface, that value is about 1,368 watts per meter squared. Q moon and Q earth are planetary infrared emissions and possibly reflected sunlight, or albedo. Q internal includes internal heat sources like electronics and batteries. These values are given in watts per meter squared here because they represent heat flux, or energy per unit area. To get total power in watts, which is what Q wants to be in, you'd multiply the spacecraft's effective cross-sectional area. Heat leaves the spacecraft defined by the term Q out, which is a product of these different variables. Emissivity as a function of wavelength times the Stefan-Boltzmann constant multiplied by temperature to the fourth multiplied by some cross-sectional area that is being radiated out. The radiation area is typically different than the illumination area, which is in here. The next step in this heat balance is equating Q in to Q out. If the heat going in is the heat going out, then you can move the different terms of the equation to isolate temperature and Q out to the left-hand side of the equation and solve for that. That's one equation and one unknown, assuming all the parameters are known or estimated. But remember, this is a single node approximation. It doesn't capture the variation between hot solar panels, cold wheels, or shaded cavities. But it gives you a good first-order check on whether your spacecraft is generally running hot, cold, or within bounds. Try computing worst-case hot, so a scenario in which there's full sun and the Earth's in view, and then a worst-case cold, in which a no sun, no Earth, and minimal internal power. In the assignments for this subsystem, I want you to compute the worst-case hot scenarios and cold scenarios for this spacecraft. It's generally a good idea to compute the worst-case hot and worst-case cold scenarios for your space robot. The hot scenario is the case when your space robot is in full sun, the Earth is in view, and all of your components are on and generating waste heat. The cold scenario is when your space robot is in eclipse or nighttime, there's no Earth in view, and you have minimal internal power. To calculate that Qint, or internal heat, of this space robot, I like to put together something called the heat budget, which is very similar to your power budget, but specific to the power not used towards the component's function. This waste power becomes heat. So let's walk through how to build a heat budget using the Artemis CubeSat heat budget as an example. This table helps you estimate how much internal heat is being generated by each component. Critical information for designing a thermal control system. This first column here is power usage. This table should be familiar to you if you followed the exercise in the electrical power subsystem where you created a power budget. The first few columns are the subsystem, the component, the part name, and then the power usage, which we extracted from each component's datasheet or manufacturer documentation. Be careful to use the worst case scenario or peak power draw if you're designing for thermal extremes. Now that new column, end efficiency, this represents how efficiently the component converts electrical power into useful work. For example, a radio transmitter can convert 30% of its power into an RF signal, and the rest becomes heat. If a component's primary function is heat generation, like a heater, its efficiency might be close to 100%. If you're unsure about efficiency, assume conservatively. For many electronics, efficiency is between 70 and 90%, meaning as much as 30% of that power is lost to heat. The product of power usage and end efficiency is heat generation, which is that far column, and that's the most important column for us in thermal design. You can calculate it using the formula up here, where heat generation in watts is equal to power usage in watts times 1 minus the efficiency in percent. So if your component uses half a watt and is 90% efficient, it generates 0.5 times 1 minus 0.9, and that's equal to 0.05 watts. Once you fill in this table for all of your subsystems, you'll be able to sum up the total internal heat load, which is in this bottom row. So once you've done your point mass thermal checks, the next level of fidelity is to build a finite element model to capture the spatial and temporal variation of temperature across the spacecraft. This lets you simulate not just a single temperature, but how heat flows through different materials and how temperatures evolve over time and space. On the left is a schematic showing all the inputs that go into a high-fidelity thermal model. You'll start with satellite geometry and orbit definition and attitude. This defines where your robot is and what it's exposed to. Then you add a library of physical material properties like thermal conductivity, heat capacity, emissivity. Next are radiation models like view factor computation, which handles how surfaces radiate or receive heat from each other. Combine these into a thermal network, apply boundary conditions, and couple it with models of internal heat generation and conduction. The solver marches forward in time to compute the temperature evolution. More model detail equals more physical accuracy. Just like a structural finite element model, a model consists of many thousands of interconnected nodes with their own temperatures and heat exchanges. In this bottom left picture, you can see a finite element cell. The spacecraft is divided into thousands of tiny elements, or voxels, each with nodes. At each time step, the solver computes temperature at each node by balancing heat in and heat out, conductive, radiative, and internal. The primary variable is temperature, one unknown per node. The heat flux is calculated as a gradient of temperature and is typically less accurate, so we refine the mesh in regions where flux changes rapidly. On the right is a thermal model analysis of the International Space Station. This color map shows surface temperature across the structure, with warm and cool zones depending on solar exposure and internal heat loads. These simulations help engineers identify hot or cold spots. They help validate component placement, they help size radiators, heaters, and insulation, and they help simulate eclipse periods, attitude changes, or payload activity. So finite element thermal analysis is how we go from the back of the envelope estimates to high confidence spacecraft performance. It's grounded in physics, driven by data, and necessary for missions where temperature distribution matters, like complex science payloads or long-duration operations. You can build the most detailed thermal model in the world, but in the end, the highest form of verification comes from real testing, replicating space-like conditions in a thermal vacuum chamber. On the right, you can see the Euclid satellite being tested in one of these chambers at Thales Alenia Space. This is the closest we can get to simulating the space environment on Earth. A thermal vacuum chamber provides high vacuum, replicating the absence of atmosphere in space. It replicates radiative and conductive control, simulating sunlight, eclipse, and orbital heating and cooling cycles. And inside, spacecraft components are exposed to the same thermal loads they'll face in orbit. The system is instrumented with thermocouples to monitor temperature responses in real time. Let's break down the tests that you might want to run. Thermal cycle tests are performed at ambient pressure. This test cycles hardware through hot and cold environments to detect material or workmanship flaws due to thermal stresses. Thermal vacuum tests are like TCT, but in high vacuum, used to verify performance under space-like conditions and run functional tests while exposed to temperature extremes. Thermal balance tests validate the overall thermal design of the spacecraft. The goal is to ensure your system stays within safe limits. This test is also used to verify thermal deformation and update thermal models based on real data. And lastly, the vacuum bakeout is used to drive off volatile contaminants from materials. This prevents outgassing in orbit, which could cause contamination or performance degradation. These tests help you evaluate real spacecraft behaviors like thermal expansion, component warm-up and cool-down lag, outgassing rates, and realistic heat transfers across the structure. Importantly, the temperatures measured during test are compared directly with the finite element thermal model predictions we were talking about earlier. This helps you refine your model and improve future predictions. Testing is expensive, but it is the most direct way to know if your spacecraft will survive and operate in space, and a critical step in closing the loop between simulation and flight performance. So hopefully, I've equipped you with a breadth of knowledge to define the function, typical requirements, design considerations, and verification methods. And I hope that you've also understood a survey of various technologies associated with the thermal control subsystem. See you in the next one.